All right. So here we have a couple of functions, and we're asked to determine if these functions are continuous on the interval between 1 and 4. All right. So again, here we have x squared. F of x equals x squared. We're very familiar with what that looks like. And it is continuous. Now, in order to prove that it's continuous, we need to prove that it's continuous at every point on that interval. And so how do we do that? How do we do that? How do we get an infinite number of points between 1 and 4, right? You know, you've got 1, 2, 3, and 4, but you've got, well, I guess not necessarily 1 and 4. The endpoints don't appear to be included, but, you know, we've got 1.5, we've got 1.499999, we've got 3.6284964. You know, there's an infinite number of points between 1 and 4. And so how do you prove that this is continuous? Okay, you would have to test every point, right? By the definition, this function is only continuous on the interval if it's continuous at every point. So there is actually a very formal, rigorous way to prove this, but we're not going to go there. Not in this class. We're not going to go there. If you decide to become a math major, maybe you'll learn how to prove continuity at any point. I realized I didn't spell continuous right. Sorry. But continuous. Okay. But so what we're going to say, we know that f of x is defined, right? It's defined at every point. Defined for all values of x, all values on the interval, right? On the interval 1 less than x less than 4, right? It's defined for all the values between 1 and 4, right? Because we can plug in any value we want to into x squared and get a value for the output. And now that this is where it gets a little bit shaky, I'm just going to say that the limit as x approaches any value a of f of x, right, is equal to f of a. Okay, that's where it gets a little bit shaky. So for all values of a between 1 and 4. Okay, so again, proving this, it requires a little more rigor, but we're not going to go there. And actually, any power function, all power functions, every power, all power functions, I'll just write it in here. So all power functions are continuous. We'll just make that assumption. Continuous. All right. And by extension, we can also say that, let's see, that was supposed to be all polynomials, because that's just a sum of a bunch of power functions, right? Polynomials are also continuous. Okay. Right, because they're defined at every point, and if we picked any points in any interval, really, that doesn't have to be 1 to 4, because this function is defined for all values of x from negative infinity to infinity. And if we picked any one of those and we tried to sneak up on it from either side, we're going to get the same limit. So the limit exists on either side of any point, and it goes to that same value. All right. So for the most part, for the functions that we know, we just need to know where those functions are not defined. All right. So if we look at the next function, 1 over 2x minus 6. Now we have a little problem at 3, right? When x is equal to 3, I'd get 1 over 0. And so this function is not defined at 0. So this function is not continuous. It's not continuous, and it's not continuous at x equals 3, right? So f of x is undefined at x equals 3, right? We can't put in x equals 3. We could sneak up on either side, and if we look at the limit as x approaches 3, of this f of x function as it approaches 3 from the right, right? So values of 3 that are a little bigger than 3. So 2 times 3 is going to be a little bigger than 6. And so we're going to get positive infinity. It's going to go to positive infinity. And if we look at it from the other side, as x goes to 3 from the left, right, then, okay, so we're taking values that are a little bit smaller than 3. So 2 times x is going to be a little smaller than 6, and so we're going to get negative values in the denominator, and it's going to go to negative infinity. So you can see, obviously, that the limit doesn't exist, and also the value of the function doesn't exist. So it can't be continuous. All right. So for the most part, when you're asked to look at the continuity of a function over an interval, you're just looking for any breaks or jumps or holes in the function, and or if any place where it's not defined, and that's going to determine where it's not continuous. All right, and we're not going to get too much. We're not going to get too rigorous about our proof of continuity for functions right now. So, all right. Well, the next thing we're going to talk about is the derivative. This is the the finale here. And so I'll meet you in the next video to talk about the derivative of a function using limits and continuity.